This is Step 1, 2011, Question 7. We are told that the water tank has a height of water h at time t, and its initial height of water is big H. Water flows into the tank at a constant rate, and water flows out of the tank through a hole at the bottom at a rate proportional to h, the height of the water at the time. We are also told that the height of water remains constant at h equals alpha squared big H, where alpha is a constant greater than 1. So the first part of the question asks us to show that dH dt, so the rate of change of the height with respect to time, is equal to k times alpha squared h big H minus h, the height of the water at the time t, where k is some constant. So the first thing we need to do is find a differential equation to model the situation of water flowing in and out of the tank. So the way we do this is we say that dH dt is equal to the rate of water flowing into the tank minus the rate of water flowing out of the tank. We know that the rate of water flowing in is constant, so we can just call it some arbitrary constant, b for example, and that we know the rate of water flowing out is proportional to h, so it's a constant times h. So if we just choose a constants b and a, we get dH dt equals b minus ah, where b and a are arbitrary constants for now. Now remember that we're giving another piece of information. We're told that the height of water remains constant at h equals alpha squared h. So what can we deduce from this? Because we need a way to relate the a and b constants, because this expression only has one constant. What we can deduce is if a height of water remains constant, that means that dH dt equals 0. So dH dt is 0 when h equals alpha squared h. So if we plug this into our differential equation here, we get 0 is b minus a times alpha squared h. So we get a relation between b and a. And now we can sub this expression for b back into dH dt. So we get dH dt is a times alpha squared h minus a h, where remembering that I'm saying that that's big H. And if we pull out a constant a, we can relabel the a as k, and we get dH dt is k times alpha squared big H minus h. And that is exactly what we were looking for in the question. Now we're asked to deduce that the time taken for the height to reach alpha big H is given by kt equals ln 1 plus 1 over alpha. Now let's look back to our differential equation. So we have dH dt equals k alpha squared big H minus h. And what we want to do to solve this differential equation, the easiest thing to do is separate the variables. So by separating the variables, we get 1 over alpha squared h minus little h dh equals k dt. Now, because we want to find the time taken to reach a certain height, the best thing to do is integrate between limits. So we want to integrate between h and alpha h here, because the height goes from h to alpha h, and we want to integrate between 0 and big T here, because time goes from 0 to t. So taking that integral between each of the limits, we get this equation here, and if we integrate both sides, we get this being minus ln alpha squared h minus h, the negative comes from the minus here, evaluated between h and alpha h equals kt. And then if we evaluate the left hand side, we get minus ln alpha squared h minus alpha h plus ln alpha squared h minus h equals kt. We can put this under a common logarithm, getting ln alpha squared h minus h over alpha squared h minus alpha h. We can actually eliminate the h from here, getting ln alpha squared minus 1 over alpha squared minus alpha equals kt. And then factorizing using difference of two squares, we get ln alpha minus 1 times alpha plus 1 over alpha minus 1, and then we can cancel the alpha minus 1s to get ln alpha plus 1 over alpha equals kt. And this can be separated inside the fraction to ln 1 plus 1 over alpha equals kt, which is exactly what we were required to show here. Finally, in this part, we're asked to
deduce that kt is approximately 1 over alpha for large values of alpha. And at the start of the question, we're also told that we can assume that ln 1 plus x is approximately x minus half x squared when the modulus of x is small. So let's look at our expression for kt. For large alpha, we can say that 1 over alpha is small. So we can expand this ln 1 plus 1 over alpha as we expand it here, getting 1 over alpha minus a half times 1 over alpha squared. And noting that the 1 over alpha squared is going to be even smaller than the 1 over alpha, then we can get an approximation of just 1 over alpha. And this suffices for this part. So for the second part of the question, we have the same setup as before. However, now water leaves the tank at a rate that is proportional to root h, where h is the height of the water in the tank at time t. And we have the same condition that height of water remains constant when the height of the water is alpha squared times big H, where big H is the initial height of the water. So we're asked now to show that the time taken t dash for the water level to reach alpha H from H satisfies this equation here. So first of all, the first thing we need to do is, just like before, because we're doing the exact same thing as before, but now with a different rate of water leaving the tank, we need to form a differential equation. So remember, to form a differential equation of dH dt, we need to consider the rate of water flowing in and taking away the rate of water flowing out. So have a go at doing this yourself and trying to form a differential equation like we did before using the conditions. So this involves two steps: forming a dE with arbitrary constants like we did before, and then using the dH dt equals 0 condition to eliminate one of the constants. So pause this video and have a go yourself. Okay, let's have a look at what we get. So we have dH dt is d, some constant, minus c root h, where the constants are positive. So using the condition dH dt is 0 at h equals alpha squared h, we get d equals c alpha root h. And then subbing this back into our dE, we get dH dt is c alpha root h minus root h.
So here's our differential equation, which we need to solve to find t dash. So like before, we want to integrate between limits of both sides. So I've separated the variables here and integrating between h and alpha h on the dH side and integrating between 0 and t dash on the dt side, so we can calculate the time that it takes for h to reach alpha h. And so we'll look specifically at the left-hand integral because it's a lot more complicated now. So looking at the left-hand side, we have this integral here with a root h here. Now, there is no standard way to deal with this directly, so the best thing to do is to make a substitution. So let u equals root h. So we get du dh equals 1 over 2 root h, which is 1 over 2u. And the limits alpha h becomes root alpha h, and the limit h equals root h. So making this substitution, we get this new integral, and then simplifying it down, we will first notice that there is a u on the top and the u on the bottom, so we can split this into partial fractions. So have a go yourself at splitting this integral into its partial fractions. There will be a number term and a fraction term as well. Okay, so splitting this into a number and a fraction term, because note that we have the same order on both the top and bottom, we get the integral between root h and root alpha h minus 2 plus 2 alpha root h over alpha root h minus u. And this is a standard integral, which is the log integral. So we just integrate this, getting minus 2u minus 2 alpha root h ln alpha root h minus u, evaluated between root h and root alpha h. And then if we just evaluate this out and expand it out, we get this huge expression. So have a go yourself and check that you get the same thing. And then we can take out a 2 root h out of all of these terms. So taking out 2 root h, we get 1 minus root alpha plus alpha ln alpha root h minus root h over alpha root h minus alpha root alpha h. And here again we can take out a root h. So we get 2 root h times 1 minus root alpha plus alpha ln alpha minus 1 over alpha minus root alpha. Now this is really similar to previous, but we had an alpha squared here instead. So what we can actually do is still apply difference of two squares, because this is just difference of two squares of root alpha. So we get root alpha minus 1 and root alpha plus 1 on the top, and we can pull out a root alpha from this bracket. this gives us 2 root h times 1 minus root alpha plus alpha ln root alpha minus 1 root alpha plus 1 over root alpha minus 1. And these brackets cancel, and this bracket goes to 1 plus 1 over root alpha, and so we get 2 root h times 1 minus root alpha plus alpha ln 1 plus 1 over root alpha as the integral on the left-hand side. Note that our integral on the right-hand side is just ct. And so we can just write ct dash is this expression, as asked for in the question.
And then finally, we are asked to deduce that ct dash is approximately root big H for large values of alpha. And we can also assume this expansion here. So let's do as we did before and expand this out, because we know that since alpha is large, 1 over root alpha will be small. So we get an approximation 2 root h 1 minus root alpha plus alpha times 1 over root alpha minus a half times 1 over alpha. And then multiplying this, we get alpha over root alpha, which is root alpha. And then alpha times 1 over 2 alpha minus 1 over 2 alpha, which is minus a half. And then these root alphas cancel, and we get just a half in this bracket. So we get 2 root h times a half, which is just root h. So ct dash is approximately root h for large values of alpha as required. And then that's the end of the question.